Ayan, thank you for spending your time together with us to learn about quantum computing. All right, so we're very excited to for this session. Last time we introduced quantum computing to you and even some approaches that we do so that we can apply that on a hardware level. But this time we're gonna step back a bit and learn a bit more, have a review on math, programming, and maybe we can start on creating your first quantum programs. So again, some session norms. We encourage everyone to engage actively, immerse yourselves in this learning experience, no, and be open. We're here to have a meaningful conversation with each other. Ask away. There are no dumb questions. Don't be afraid to ask when you need to, and of course, to respect everyone. Let's give each other our undivided attention. So, before anything else, we have some reminders. If you have some questions or yeah, we've disabled the chat function here at Zoom, and we encourage you instead to go to our Discord server and use the live questions channel in there, just so that if there are still some questions unanswered during our live session, we can put your answer. We can put the appropriate answers or even send some resources asynchronously in Discord. All right. So before anything else, let me ask you this. Ayan. Let me ask you this. If you're given a television and 12 hours for yourself, which will you watch? Ayan. A would be 12 1 hour long episodes of the series of your choice, or B, 6 of 2 hours movies of your choice. So again, we can utilize the Discord live questions. Ayan, may nag-direct message sa akin. A daw siya. Hello. Ayan. So more on series. Ayan. So personally ako rin series. So wait, I just send a message dun sa live questions. Ayan. Sige. Okay. So you can send, lipat tayo doon just so that kung may questions kayo, ayan, dyan natin makita. And if masagot, di ba? Sayang kasi last time we had some insightful answers to your questions and nawala na sila nung natapos na yung Zoom. Pero, ayan, kabalik natin, di ba? Like, after this session, we can go back to those questions. Ayan. Ayan, so halo-halo, merong B, merong A. Ayan, ano yung pinapanood nyo? What are you watching? Anong series? Ayan, ilagay nyo na rin dyan. Anong series, anong movies yung pinapanood nyo lately? So, ayan, Full Good Omens rewatch daw. Ayan, sabi ni Josh. Ayan, may mga letter A, may mga letter B. Ayan, sige, ano yung mga pinapanood nyo? Ayan, sa amin kasi tapos na yung midterms namin. So, I'm looking for something to watch this weekend. No? Although marami pang gagawin. Pero yes, ayan. Nowhere. Ayan, sabi ni Romil, Nowhere. Ano yung movie ba yon or series? Better Call Saul. A. Beckham. Peaky Blinders. Hindi ko man natapos yung first episode. Pero yeah, babalikan ko yan. Sige. That's nice. That's nice. Okay. Sige, ayan, may nagtatype pa. Sige, go lang, guys. Send your message there. Oh, right. Ayan, meron pa. Sige, go lang. Hello, hello. Hope na okay lang kayo sa inyong mga pamamahay or kung nasa labas kayo man kayo, ingat kayo. Okay. All right. Okay. Thank you for your active participation. Just some reminders, no? Accomplish the onboarding checklist which was sent on your emails. So it looks like this, yung picture natin on the side. And we also put like your status if you have or if you haven't dun sa mga forms that you need to fill in. So we will send another update this week since I saw na some of you already accomplished those forms, so you would see it reflected on the next batch of emails that we will send. All right. So for the homework, reminder that your homework is due on October 25. That is on Wednesday, if I remember correctly, at 11:59 p.m. So that would be your homework for week 1. Okay. For those that already answered, we will actually return your scores, your outputs back to you so that you can iterate on your answer. So if you have better answers, or if you know now, no, at nalaman niyo na kung ano yung tamang sagot, just so that yeah, we don't want this to be stressful, no. We want you to learn as much as possible, and no pressure naman. So we would probably return this tomorrow or on Monday. So look out na lang so that you can edit your submissions as well. Okay. So yeah, we also encourage you to collaborate. So we've added some channels on Discord. So if you can see homework help, or you can have, we have some study rooms. You can talk to other people, talk with your peers on your schools. If you want to meet face to face, that's also fine. Pero yeah, if you have extra time, and you want to do your homework together, you want to learn together, please use our channels there. Okay. So for today's video, for today's lecture, so we're gonna talk more about crunching the numbers, the mathematics essentials. So we would have a review of that, about complex numbers, vectors, matrices, binary numbers, logic gates, and probability. And then we would have a short basic programming introduction again, and getting started with IBM Quantum Experience. Okay, so before that, our president in One Quantum PH, Sir Bobby, have some tips and have some things to say. Hello po, Sir Bob. Good afternoon.
Salamat, Javis. So hello guys. So thank you once again for attending the second session. And the topic for this session is it's really more about reviewing the mathematics. So in quantum computing, it's the essential mathematics that you need are um, the linear algebra, and also the probability, because when we measure qubits, it gives us a probability. And in order for you to be able to construct logic gate circuits, you need to learn about logic gates. So especially those people who are going to be were selected to be in the hackathon, it's very important that you master this aspect, because many of the hackathon questions are, asking you to, for example, given this A and B or C, create a circuit out of it, and you know, so yeah, it's very important that you learn that. Yeah, and also binary numbers. If you're not familiar with them, we're going to cover them as well. And in the next session, the next lecture of the session, we are going to introduce the Python programming. If you're not familiar, but if you're familiar, you might just just listen. But we just want to make sure that everyone knows the basics, so that, because we are going to use this in the in our fourth session. And finally, the last lecture of this session will be getting started with IBM Quantum Experience. Yeah, so that's it. Back to you. Thank you.
Thank you, sir. So as we've said from before, we want you to have the proper fundamentals, proper background, so that you can start building your circuits. All right. Okay. Now at this juncture, we would like to start our first session for today. Okay, so we want to introduce our speaker for tonight, for this afternoon pa pala. Ayan. So, Sir Elmer Paramo. So, Sir Elmer is a senior research specialist at DOST, ASTI. He has extensive knowledge and experience in machine learning and artificial intelligence. He's currently pursuing a PhD in computer science at De La Salle University and holds a master's degree in electrical engineering from the University of the Philippines. He manages diverse AI projects in weather forecasting, agriculture, NLP, construction, healthcare, and more. And he is also dedicated to driving innovation through AI and committed to advancing quantum computing in the Philippines. So, let's give it up for Sir Elmer. Hello po.
Hello, thank you, Jabez, for that introduction. Good afternoon, everyone. Yes. Am I being heard? And can you see my screen?
Yes, loud
Okay,
and clear
thank
po.
you. Yeah. Sige, I will take a stab at sharing with you what my knowledge about the mathematical preliminaries in quantum computing. So perhaps if there are some topics or uh, and some concepts that are not clear, perhaps my colleagues here in One Quantum Philippines can will also help me in explaining then if not now, maybe in their respective lecture. So to start, I'll be just like what Sir Bobby mentioned. I'll be talking about vectors and matrices. So basically, these are topics in linear algebra. Also talk about basic logic because later on we'll be discussing more on circuits. No, and another important thing, very important concepts that we need to know is concept of complex numbers, and I'll also talk about a little bit of probability theory. So let's start. We have a lot of things to cover, so I'm gonna start with vectors. Um, my idea when I first heard about vectors, actually, it was during my high school years during a physics class during my high school. So that this is where uh, vectors was first introduced. So during that time, my idea of a vector is anything. It's a quantity with a direction and a magnitude. So usually we draw them and geometrically represented by an arrow. So during that time, that's my conception of what a vector is. But later on, my that idea of a vector actually well, when I studied applied mathematics in University of the Philippines in Los Baños, our professor asked us what a vector is, and then I recited. I actually did define vector as what my physics teacher would have me define what vector is. But a lot of my classmates actually laughed during that time. Even my professor actually grinned. So because during that time I didn't have the full idea of what a vector is. So basically a vector you can define vector from different viewpoints. You can from the physics perspective you can define it as a quantity with direction and magnitude, but from the computer science perspective we can think of a vector as just an array of numbers or an n tuple. But more abstractly, so this is my favorite definition and the abstract mathematical perspective, any object or entity that can be added together or scaled, okay, or scaled or multiplied by scalar to produce another object of the same kind. So that's the abstract way of defining what a vector is. So in that case, I remember my professor asked us, do you think a halo-halo is a vector? By the way, a halo-halo is that dessert we have here in the Philippines where it is it's composed of banana, sweet langka or sago or what a lot of things there, and it's very delicious. So if you add two halo-halos together, the output is another halo-halo. Or if you actually multiply a halo-halo by five, you will have five halo-halo, and if you could combine them, it's still a halo-halo. So basically, anything that can be scaled and added together to produce of the same kind is a vector. So we can think of a polynomial with degree 5 or lower as a vector because you can add two polynomials together and you will end up with another polynomial. We can add all three any 3x3 matrices. So that's also considered a vector, because when you add two 3x3 matrices, the resulting output is also a 3x3 matrices. So when you multiply a matrix by a scalar, the answer is also a matrix. So basically, that's the thing how we talk about what vector is. So vectors have dimensionality. We can think of, we can actually represent vectors in 2 dimensions or even in 3 dimensions. And another thing is we can actually have vectors represented in several dimensions, more than 3. But I think it's really hard. It's really difficult to wrap our hands around visualizing dimensions greater than 3, because we live in a 3-dimensional world. But there are other vectors. We can consider vectors with dimensions higher than 3. So, and vectors have components. We can represent a vector by its component form. So basically, just like the computer science perspective of definition of vectors, you can represent a vector by an array of numbers. So in this case, it's a 2-dimensional vector. You represent them by an ordered pair, V1 and V2. For a 3-dimensional vector, you represent them by the ordered triple, and so on and so forth. So you can represent basically a vector by its component. It's an ordered n tuple. And another important properties of vector is vectors have magnitude and direction. So going back to the definition, to our physics perspective, mathematically we can define the magnitude as, or sometimes in other literature you will hear the word norm, or norm. And later on, when we go to complex numbers, the operations on vectors will come in handy. So the magnitude or the length of a vector is a non-negative scalar with this formula. So if you still remember your analytic geometry, when we want to compute for the distance between 2 points, so basically that's the Euclidean distance, that's the norm. That's really how we compute the norm or the magnitude of a vector. Now, with regards to the direction basically is this unit vector called the direction. We just have to divide the vector by its magnitude. So that is the direction. So basically, it's a unit vector showing you the direction of that vector. So essentially, you can define a vector as the product, or the product of its length or its magnitude and its direction. And vectors can be added. That's just like what the abstract mathematical perspective, anything that can be added and scaled, okay? So geometrically, we can interpret the addition of vectors just by, for example, if we represent a vector by an arrow, by 2 arrows, for example, so we just place the tail of the second arrow to the head of the first arrow, and then from the origin, you just draw that arrow from the origin to the head of the second vector. So basically, that's the resulting vector. That's the resultant vector. So that's vector addition. And scaling a vector is also possible. So if you have, basically scaling a vector is just multiplying that vector by a real number. So in this case, if you multiply a vector by a number greater than 1, so effectively, you're extending that vector. You're lengthening that vector. In this case, if you multiply vector u by 1.5, so the length of that vector now becomes 1.5 longer than the original vector. You can actually multiply a negative number, but effectively, if you multiply a negative number to that vector, it goes to the other direction. For example, in this case, you multiply a number by negative 2u. So by negative 2, so it means that the vector will be twice as long as the original vector, but it is pointing now in the opposite direction. Now, because of the multiplication of a negative number or the scaling of a negative number, you can define actually vector subtraction. So vector subtraction is just vector addition coupled with the multiplication or the scaling of a negative number. So you can define vector addition in this case. Vector subtraction, I mean. So far so good. Okay. Now, this is also another important operation in for vectors, the dot product. So basically, if you have two vectors, u and v with corresponding components u1, u2, u3, and v1, v2, v3. So the dot product is a scalar. So basically, you have two vectors that your operands are two vectors, but the resulting the result will be a scalar. It's not a vector. So, and it's being done by you just multiply correspondingly each of the component of each vector, and then you add them together, so you get that product. And that product will, it is geometrically the dot product has a geometric interpretation. Let me just go back to the previous slide. As you can see here, you can actually define that product in terms of the angle between two vectors. So, for example, in this case, as you can see at the showing here at the upper right, so it forms a triangle. You can use the law of cosine. So let's just review the law of cosine. It's just a generalized formula for the Pythagorean theorem. We have the c squared equals a squared plus b squared minus 2 times ab cosine the angle between those two sides, no? Between the two sides, so cosine theta. So that's our law of cosine. So using that, you can actually derive the formula here. So cosine theta will just be the dot product of two vectors divided by the product of their magnitudes. So this one, it is not the absolute value, it is actually the magnitude of two vectors. So basically, you see here that theta of the dot product of two vectors divided by the product of their norms. So what is the implication of this? So in actually my field is NLP. We use this for measuring the similarity between two words. So in if you can see, this is cosine, and the behavior. Let's review the behavior of cosine. Cosine, the values of cosine ranges from -1 to +1. So at 0, it's actually +1. Okay, so meaning if your angle is 0, okay, cosine theta, it means that you have the maximum value, which is 1. Okay, but if your theta is actually 90 degrees or pi over 2, okay, pi over 2 radians, if your theta is pi over 2 radians, meaning they are at right angle, that the vectors are at right angle to each other, or in technically they are called orthogonal. Okay, so the cosine of 90 degrees or cosine of pi over 2 is 0. Okay, so meaning if two vectors are orthogonal or at 90 degrees to each other, okay, the cosine, the angle between them, or basically is 90 degrees. So the cosine theta is equals to 0. So there's an important implication of that concept. Okay. Next, so let me just define equality between among vectors. Two vectors are equal if they have the same length and direction. Now let me introduce to you a new notation for vectors. So we've been in the previous slides, I've been using a boldface lowercase letter to represent vectors, but I'm going to introduce to you another representation which will come in handy when you which will become familiar to you if you are dealing with quantum computing or quantum mechanics. This is the ket notation. So from here on out, I'm going to represent a vector. So in this case, this is a column vector using the ket notation. So as you can see here, this is ket A. It's a vector 3, 2. And ket B, column vector 1, -2. So this is a special notation called the bracket notation. And you're going to use this notation more often because in quantum computing. but some of my colleagues will be talking more about that in later lectures. So for vector addition, you can see here, let's see, A plus B, or ket A plus ket B equals ket C. So you can see ket A is 3, 2, ket B is 1, negative 2, and the resulting vector is ket C 4, 0. So you can, geometrically, you can see that ket A is, ket C is just the sum, or basically if you connect the vector or the arrow, the tail end of the arrow of B to A, it will result to the vector C. So that's vector addition. Scalar multiplication, the same thing. You just multiply a vector by a number, in this case 2. So 2 times the vector 1, negative 2. So that's 2, negative 4. And since we already know how to do addition and scalar multiplication, which are the two important properties of vector, of two important operations for vectors, okay, we can now define what a linear combination is. We actually do a lot of linear combinations. Linear combinations, you do linear combinations if you're, for example, computing for grade for teachers. You have, for example, one criteria for recitation, or one for project, for quizzes, and then you have percentages for each one. So you multiply times the score of the student. You multiply for quizzes times by the score of an for example, recitation and so on, and then you add them together. So that's basically linear combination. Another thing, if you're judging, if you judge for example, a contest or a poster making contest or some sort, you have some criteria, and then each criteria has certain percentages. So you give them a grade. So you multiply that percentage to that the grade that you give for that piece of work, for example, and then you add them together. So basically, that's a linear combination. The same way for vectors, since we already know how to do scaling, or multiplying by scalar in addition, let's combine them together. So we call that a linear combination. So in this case, ket C is a linear combination of is the product or a scaled version of ket A, and ket B is a scaled product, or the scaled version of ket B. We can combine them together. If we add ket C and ket B, we will see here, this is a vector example of linear combination. So vector E is a linear combination of A and B, meaning that we have a scalar times a vector plus another scalar times a vector. So basically, that's a linear combination. So linear combination is just adding a scalar, adding together a scale version of another vector. And this is very much related to the quantum mechanical concept of superposition, or sometimes linear superposition. So for example, if we have here, later on, you will be introduced to special basis vectors like ket1 and ket0. So these are standard basis vector. Ket1 is a specialized vector which is represented by 0, 1, and ket0 is a specialized vector represented by 1, 0. And as you can see, since they are standard basis vector, you can actually, any vector can be represented in 2D. In this case, in two-dimensional space, any vector can be represented as a linear combination of these two vectors, ket1 and ket0. So here is this will be explained later. Since, for example, in this case, I'm just trying to explain to you what a linear combination is, or a linear superposition. So ket E is equals to the 2 times ket A plus 2 times ket B. So meaning that ket E is a linear combination, or a linear superposition of ket A and ket B. So usually when we go to cubics, when they discuss cubics, they will be able to show that for example, a cubic state psi is just a linear combination of 0 and 1. Yeah, with the scalar alpha and beta. Okay, so any question at this point? Let me just check. Do you have question? Okay. Okay, I'll continue. Now let's go to the matrix. I'm not sure if you're familiar with this, but during the late 90s and early 2000, this is a very familiar screensaver that we used during those times. So because of that movie, The Matrix, starring Keanu Reeves. But what is the matrix? So a matrix is basically a rectangular array of numbers or symbols or expressions arranged in rows and columns. So coming from vector, now we study matrix. So we have here a matrix is just a rectangular representations of number, but it has a lot of geometric interpretation also. So as you can see here, this is an example of a matrix. We use matrix during algebra when we try to solve systems of linear equation. We represent them as matrix, and then we do the Gaussian elimination. So that's where I first encountered the matrix. So this is an example of a real valued matrix. So it has 5 columns and 4 rows. So notation of the matrix, we usually use a capital letter to represent a matrix. As you can see here, by convention, yung first element is usually A11, and then for the first row, A12, A13, and then A21, A22, A23, A31, A32, A33. So that's how we represent a matrix. But matrix can have several dimensions. So this is a square matrix. It has the same number of rows and columns. So this is an example of a real valued matrix. And matrix can be redefined as actually based on the vectors that we studied earlier. So this is a column vector, and this is a row vector. So let's if we can add matrices, if we can add vectors, we can also add matrices. So this is just straightforward. We can add matrices by element wise, meaning each corresponding element will be added together to form the resulting matrix. So in this case, for the matrix addition, you can see here A11. Also, this is A plus B. So matrix A is this matrix here, composed of the different components A11 up to A33, and matrix B is this matrix here, composed of B11 up to B33. So if you add them together, A plus B is the resulting matrix is A11 plus B11 up to A33 plus B33. So that it's just straightforward. And you can see matrix addition is commutative, meaning A plus B is also the same as B plus A, since element-wise you can addition is commutative. What else? Okay, example. So this is an example for matrix addition. So that's so 2, 3, 4, 5 plus 5, 3, 0, negative 1. So just the answer is 7, 6, 4, 4. Okay. So exercise. Okay. Just to check if you're still with me. Can you, or what's the answer for this matrix? So you can type your answer in the chat box by just showing me the order. Okay. So someone has already answered Okay, let me see. Okay, okay, thank you. Thank you for your answer. So let's see what the answer is. So the answer is, all right, 3336. Okay, next. Now let's go to multiplication, matrix multiplication. I mean scalar multiplication. So you can multiply a matrix by a scalar or by a real number. So it's just straightforward also. You can just multiply it, each multiply the scalar by each element in the matrix. So you can see, I think you get the idea. So let's see, I think an example here. Okay, 3 times the matrix 4, 7, 2, -3. So you can see there, just multiply each element of the matrix by that scalar. So the answer is 12, 21, 6, -9. I think that I have an exercise for this one. How about this one? Can you do this for me? Okay, okay, okay. See if your answer is correct. There you go, 9, 12, 60. Very good. Thanks for to all those who take a stab at the exercise. So now another important uh, operation on a matrix is called transposing a matrix, so or the transpose of a matrix. So if A is equals to this one, so basically transpose is just your rows will be converted to columns. So it's really hard for me to explain, but better if I'll just show you an example. For example, if this is your matrix A, so A11 up to AMN, so then the transpose will be A11, A21, and so on. And then, so basically what happened here, if you're writing by rows, okay, this time you write you write first, if you're writing across rows, this time you first write down by column. So A11 and then A12, A11, and then once you already finish the first column, you write the next column. So instead of writing by rows, you write by columns. So basically that's a transpose. Can be easier demonstrated by an example, as you can see here. So this is a matrix. If you transpose this matrix, it will become this. And matrices have dimensions, right? So in this case, this is a 3 by 4 matrix. Okay. Now, if you transpose a 3 by 4 matrix, the new dimension will now become a 4 by 3 matrix. So 1, 2, 3, 4. So this is 1, 2, 3, 4, 5, 6, 7, 8, 5, 6, 7, 8, 9, 0, 1, 2, 9, 0, 1, 2. Okay. So this is another example of a transpose matrix. Okay. Now, just a thought. Think of a matrix in your mind that when you transpose it, it's still the same matrix. Are there matrices of that kind? Okay, actually there are. You can actually think of a matrix where the transpose is equal to itself. Yeah. Yeah, the identity matrix is one. We will go to the identity matrix later. Okay, yeah, there's another one by Sir Christian who he was able to come up with a a matrix with 1 2 1 2 1 2 1 2 1. Yeah. So what do you call that kind of matrix? Can anyone tell me what that kind of matrix is where A is equals to its A transpose? Anyone can still can tell me what square matrices whose transpose is equals to itself? Okay, it starts with the letter S. Actually, I forgot about it, and then I just Googled something, and then it validates my answer. Yeah, very good. It's called a symmetric matrix. Symmetric matrices are those square matrices whose transpose is equal to itself. Uh, okay, let's define matrix multiplication. So basically, matrix multiplication is not as straightforward as matrix addition and scalar multiplication, because in matrix multiplication, first have uh, to make sure that those two the matrices that you're trying to uh, multiply are compatible matrices. So how do you know if they are compatible? So if each of the matrix they have dimensions. For example, in this case, the dimension of the matrix is m, and I mean that the number of rows of the matrix is m, and the number of column is n, and we're going to multiply it with a matrix whose dimension is n by p. So in order to check if they are compatible, if the number of columns in your first matrix is equal to the number of rows in your second matrix then we can say that they are compatible, meaning that you can multiply. You can their product is defined. Okay. So that's the first thing that you need to know. You need to make sure that uh, those the matrices are compatible first, because if they're not compatible, you cannot multiply them. So in this case, this is an m by n multiplied by n by p. So they are compatible. Now, the resulting product of the matrix, the dimension of that will be equal to m by p, meaning the number of rows for your first matrix and the number of columns of your second matrix. So let's see. Okay, so we have here two matrices, ABC matrix ABCD, and the other matrix has elements CDZ, EFG, XZ. So to multiply them, you can see the first one is a 2 by 3 matrix and the second one is a 3 by 2 matrix. So the resulting matrix is a 2 by 2 matrix. They're compatible, you see here, because you check for we called it the mean, meaning the row of the first matrix and the column of the second matrix. And the resulting dimension of the product is the extreme. So that's 2 by 2. Okay, you can also multiply vectors. If you, for example, in this case, if you multiply a vector, this is a dot product, basically, x sub 1 to x sub n, and then y sub 1 to y sub n. This is a product of two vectors. This is bra x multiplied by ket y is equals to this one. So the same way, think of matrix multiplication as that way, but you just have to consider uh, each row and each column for the matrix multiplication. I'm just let me just see here. Okay, matrix vector multiplication. So for example, if you have here a 3 by 2 matrix multiplied by a column vector 2, 3 with a dimension 2 by 1. So this is 3 by 2 and this is 2 by 1. So they are compatible. So what will happen if you multiply them? So if this is your matrix, you can think of think of it as a column of raw vectors A, and if you multiply it with a vector, for example, ket x, you can think of it as multiplying this matrix here. So you're multiplying a column of raw vectors by each of by this x. So basically, you can think of it matrix vector multiplication using that illustration. So for example, in this case, if you have a matrix here, 2, 1, 3, 4, 4, 5 multiplied by this vector 2, 3. So 2, 1 multiplied by 2, 3, and then 3, 4 multiplied by 2, 3, and then 4, 5 multiplied by 2, 3. So let's simplify this. So 2 times 2 plus 1 times 3. So it goes here, and then 3 times 2 plus 4 times 3. That's here, and then 4 times 5 plus 5 times 3. So you have here the final answer is 7, 18, 23. So basically what we're doing is this row multiplied by this column. So that goes here. And then this row multiplied by this your vector here goes the answer will go here, and then 4 times 2 times plus 5 times 3, so that's that one here, that's equals to 23. So this is the uh, process for matrix vector multiplication. Now let me give you an exercise. So if this is your x and this is your y and this is your z. Sorry, I didn't. Don't worry. Please ignore that exercise. I wasn't able to give you an example of the matrix to multiply for those vectors. So we can also think of a matrix. So in the first part, we thought of the matrix as a column of row vectors. We can also think of a matrix as a row of column vectors. So in this case, so this is the illustration of how to multiply two matrices. So for example, you have here, this is matrix A and then matrix B. So the resulting product will be, it shows you where, what elements to multiply and add, and where the linear combination of that row and column goes. For example, in this case, this is the first row. So you do a linear combination of the first row and in this case, the second column of B. So the linear combination of the first row of A and the second column of B goes to the first row, second column element of your matrix. So in the same way here, the linear combination of your third row in the column A and the third column of column B, okay, the result of that linear combination will be your third row and third column element of your resulting matrix. So if you have here matrix A and matrix B, okay, so matrix A is 2 by 2 and matrix B is 2 by 3. So what would be the dimension of the resulting product A times B? What's the dimension? Anyone? So if matrix A is 2 by 2 and matrix B is 2 by 3, what's the dimension of the resulting product A times B? Anyone? Any from the students? 2 by 3? Say, let's see if that is 2 by 3. Yes, the answer is 2 by 3. Now, let's see. So that matrix 1, 2, 3, 4, 5, 6. So we break that into a row of column vectors. And so using that analogy or a row of column vectors, we can actually do 1 times 2 times 1 1 4 goes here, and then 1 times 2 times 2 5, the answer will go here. 1 times 2 times 3 6, the answer will go here, and then 3 times 4 times 1 4, the answer will go here, and then 3 times 4 times 2 5, the answer will go here, and then 3 times 4 times 3 6, the answer will go here. So finally, the answer is 9 to 9, 12, 15, 19, 26, 33. Okay, for the exercises, this will take a while, so I'll just show you the answer. So basically, if this is D and E, so their product is this one. So negative 1, 2, 1, 0. So negative 1 times 1, 2 times 0, and then you add them, that's negative 1. And negative 3, 0. So 3 times 1 times 0, then 3 plus 0 is 3. So on. So I hope you get the hang of the process. So basically row and then look at the columns for your second one, and then the answer will be here. For example, this is the first row, and then you get the linear combination of the first row and the first column of your next matrix. So it will go to the first component of your second matrix. So that's just a review. I'm sure a lot of you are already familiar with matrix multiplication. So properties of matrix multiplication. Unfortunately, matrix multiplication is not the same as matrix addition in terms of commutativity. Matrix multiplication is not commutative. A times B is not equal to B times A. And but matrix multiplication is distributed over addition. So A times B plus C is equals to 8B plus AC. And Matrix multiplication is associative, meaning you can group which matrix first to multiply. This is another important, but I will not be I will not be proving this, but you can check this out, or you can also prove it that the transpose of the product of two matrices is equals to I mean A B transpose is equals to B transpose A transpose. So special types of matrices, the first one I have already mentioned to you about the symmetric matrices. So those are square matrices with whose transpose is equals to itself. So these are example of square matrices, meaning the number of rows is equals to the number of columns. And identity matrices, these are examples of identity matrices. For example, for a 2 by 2 identity matrix, this is the example wherein you can see along the diagonal, they are all ones, and off diagonals, you can see all the zeros. When I say diagonal, the diagonal I meant is from the upper left to the lower right. Okay. Now it's time for a 5-minute break. Okay.
Hi, Elmer. If you're talking, you're muted.
Sorry, thank you, Sir Bobby, for that. Yeah, I was talking. I've been talking. Anyway, so this time I'll be talking about logic gates. So, uh, we will go to matrices later on, but what I just discussed with you are the basic algebra of vectors and matrices, multiplying them, adding them, and so on and so forth. So this time it's I'll just insert the topics about logic gates. So these are a very important concept in quantum computing. So this I'll be discussing classical logic gates. So we use logic gates to put together circuits that will implement algorithms such as, for example, adding two numbers. So this is actually how the our processors or computing are actually designed using gates, okay, logic gates. And the basic operations are the AND, the OR, and the NOT. So I'll just breeze through this topic. So for example, for the NOT gate, the NOT gate is actually a unary operator. So it just requires one input. For example, uh, basically we're talking with the inputs here are binary numbers, okay, meaning it's either just one or zero, okay, one or zero, but it's not actually the number one or zero, but it's just an abstraction of a two-state system, like for example 5 volts or 0 volts, or magnetic or not non-magnetic, something like that, or up spin or down spin, something like that. So it's just a representation, but basically the NOT operation or the NOT gate will just invert, okay, your input. For example, if your input is 1, so your output, if you pass it to the NOT gate, the output will become 0. So this is the symbol for the NOT gate. If your input is 0, so the output of NOT 0 is 1. Okay, so that's just as simple as that. For the AND gate, this is a binary operator. So you have two inputs. Okay. If your inputs are both 0, the output is also 0. And if your input is 1 and the other one is 0, the output is also 0. So you only get the output of 1 if both are 1. Okay, so 1 and 1 is 1. 0 and 0 is 0. 0 and 1 is 0. So this is the symbol for the AND gate. And another basic operation is the OR gate. So the OR gate basically is also a binary operator. So if your inputs are 0 and 0, the output is 0. If your input is 0 or 1, 0 and the other input is 1, so the output of the OR gate is 1. Also with 1 or 0, so the output is 1. And if your two inputs are both 1, then the output is also 1. So this is the OR gate. You have also other gates like the NAND gate, the XOR gate. So, but I'll just be so for those kinds of operation, you will have a different type of truth table. But I'll no longer be showing those to you. But you can actually search them on the internet to find the other gates. But these are the basic gates. Actually, you can define. You can actually create those gates using these basic gates. So in quantum computer, you have this circuit model wherein you have here a qubit, so and then you have here a gate, and then you have here basically an input, and then you have here a gate that will do some transformation on your input, and then you're going to have an output. So basically, this is a very important concept in quantum computing, just like in classical computing, wherein you have input of binary numbers, and then you have an operator, a logical operator, and your gates, the output. So, for example, in this case, so if we have this standard zero, a ket 0, this is represented by a vector 1, 0. and the ket1 represented by the vector 0, 1. So basically, it's just like multiplying. So we have already reviewed how to multiply a matrix and a vector. So here a matrix, X is a matrix, and you have here a vector 1, 0. So basically, X is usually it's a standard gate in quantum computing. It's represented by the matrix 0, 1, 1, 0, and then ket1. So basically, it's just matrix multiplication. So when you pass a qubit to this gate, so it will output another vector here, as you can see, 1, 0. And 1, 0, we know this as the ket0. Okay. So those are things that you will work on later. So you will have a lot of those matrix and vector multiplication. So that's why I introduced to you how to multiply a matrix by a vector. So because in quantum computing you will see those different transformation of qubits or vectors by multiplying them to by a matrix. So basically, that's how we transform one quantum state to another quantum state. So now let me just introduce you to the concept of linear independence. So for example, you have here a linear combination of different vectors, x1 up to x2. So you have a linear combination just like that. So this is just a review. We have already talked about what a linear combination is. So basically, a linear combination is if you have different vectors, you multiply them by scalar and then you add them. So that's a linear combination. So as you can see here, the following vectors are, now let me talk about the concept of linear independence or linear dependence. The following vectors are linearly dependent. This is because if you can find a linear combination of the other two to produce the other one, that's it means that these vectors are linearly dependent, meaning there exists a linear combination that can produce the other vectors. So if that is the case, then we can say that these vectors are linearly dependent. So using the scalars 3 and 2, sorry, I must have missed a, okay. The following vectors are linearly dependent because you can find a scalars or a linear combination of the other two to produce the other one. So as you can see here, using scalars 3 and 2, we can produce vectors f from vectors d and e. How about the vector, the ket0 and ket1? What do you think? Are they linearly dependent or linearly independent? So, anyway, what is ket0? Ket0 is 1, 0. And ket1 is 0, 1. Now, can you think of scalars or that when you multiply, you can produce the other? So, those are example of a linearly independent vectors. This is also another example of linearly independent vectors. Because you cannot think of, if you cannot think of any scalars that when you multiply those vectors and you add them together, it will produce the other vector, or you cannot come up with those vectors, it means that these vectors are linearly independent. Okay, so once you have linearly independent vector, linearly independent vectors, you can actually create a vector space. But before we go to that thing, let me just discuss the concept of span. Okay, when you say span, for example, in this case, 2, 2, uh, okay, let's see. So this is the graph of this is a, for example, we have this space and then the only vector that we have is 2, 2. And can you think of if what other vectors can you come up with using just this vector if the only if the only thing that you can do on that vector is you can scale it and you can add them together. For example, if this is your initial set S and it contains the vector 2, 2, okay, can you produce other vectors just by multiplying it by a scalar and doing addition on those sets. So for example, if you have 2, 2, so if you multiply it by a scalar, let's say 5, so you're going to have 10, 10. So you're going to have another vector here. So you already have 10, 10. So 2, 2 and 10, 10, you can add them together to produce 12, 12. So you have also this vector. So if you if that is the only possible operations, addition and scalar multiplication, you can produce an infinitely many number of uh, vectors using just this initial vector. So basically, all those vectors that you have, those infinite number of vectors that you've come up with is called the span of this. Okay, the span of this S or the span of S. So 2, 2 is there, 0, 0 is there, negative 3 is there. You can produce negative 3 using just this 2, 2 initially. And then you can you can generate a lot of those vectors. But the thing is, if you have this span, the only vectors that you can produce are all those vectors along this line. You cannot really reproduce the whole plane. Okay? So that is the concept of span. So you can only produce all the vector using this, all the vectors in the, you can just, all the vectors that lie on this line. But you cannot produce vector, for example, vector 1, 2. Okay? Cannot produce vector 1, 2 from that span, starting with the vector 2, 2. Okay? So what if, for example, we have these two vectors? For example, initially we have this set, P, 2, 2, and negative 2, negative 2. Okay? Can we reproduce the whole vector space or the whole vectors in the 3D space using just 2? What do you think? Let's see. So 2, 2, when we add them together, you will have sorry, for this one, 2, 2, 2, 2, and negative 2, negative 2, you cannot reproduce the whole vector space because this is actually linearly dependent on this one. This is also, you cannot reproduce the whole vector space. It's just all the vectors that you can reproduce are all those vectors along this line. So what if we add another one? Let's say this one. For example, this is our initial set. We have 2, 2, negative 2, 0, and 1. Now, I think we could have, so these are the element of your initial set here. So 2, 2, negative 2, and then 0, 1. So this one is 2, 2. This one is 2, negative 2. So now, the only operations that you're allowed to do is scalar multiplication and addition. Now the question is, can you represent the whole vector space? Meaning, can you represent any type of vector in 2D using just this elements? Actually, we can have all of these vectors by adding and multiplying. So basically, the span of view, meaning the span, when you say the span, it's all the set of vectors that can be generated from your initial set or from your set U. So if you have 2, 2, negative 2, and 1, 0, you can actually span R squared, meaning R squared is the set of all real valued 2-column vectors. So that is your R squared. So the span is, this is a set of vectors that are linearly independent, okay? This condition of linear independence for spanning set ends up being so important that we give a spanning sets for linearly independent vectors a special name called the basis, okay? So this one, 3, 0, 3, and 3, 3 is an example of a linearly independent vector. So this is an example of a basis. Meaning, if you start with this one, 0, 3, and 3, 3, just by doing linear combinations of these two, you can actually generate any other all the types of two component vector in R squared or in R2. So a very important standard basis that we can actually come up with is this ket 0 and ket 1. So this one, they are orthogonal, and you can actually come up with any vector that is a linear combination of these two vectors. Meaning, just by this standard basis, you can generate all the type of vectors in 2D space. So basically, you can generate 3, 3 here. So 3, 3 can be generated just by multiplying the first ket 0 by 3 and then adding the 3 times ket 1. So you'll be able to produce 3, 3. And think of it, any two-column vector can be generated by this standard basis. So that's the concept of basis and span. And I'll just breeze through this linear transformation. So the idea here in linear transformation is basically linear transformation is just if you have a vector space. Okay, a vector space is just a set of all the vectors in, for example, in 2D. Now you can actually transform those vectors, meaning you can change the length or rotate them or do some using a linear transformation. And the linear transformation is basically just matrix multiplication. So I will just breeze through this slide, but basically you can do those linear transform. Example of linear transformation are reflections and rotations. And reflections and rotations, basically, it's just, for example, if you have a vector pointing in one direction and you want to reflect that to another direction, basically, effectively it's just like multiplying that vector with a particular kind of matrix. So that's the essence of linear transformation. So we can represent linear transformation with matrices. So for example, here, we can actually come up with a transformation that can transform a matrix in R squared to R cubed. So these are example of linear transformation from r squared to r cubed. So linear transformation is just matrix multiplication. You just multiply a vector by a particular matrix. So this one is an example of linear transformation. It's called a reflection. So you multiply a matrix, a particular matrix, and then it will come up with a transformed version of that matrix, of that vector. And I'll just breeze through this slide. So you have translation and rotation. So basically, if you want to rotate a vector, to a particular angle, you just multiply that vector with this matrix, cosine theta, negative sine theta, cosine theta, and it will be whatever the value of theta that is going to be the rotation of that vector. And what else? Okay, let me just discuss these complex numbers. This is a Venn diagram showing you the different sets of numbers. So initially, when we were in the elementary, we were introduced to natural numbers. So those are numbers 0, 1, 2, 3. So those are counting numbers. And then when I was in high school, I was introduced to the concept of integers, that there are those negative numbers that actually we can subtract a number greater than itself. So before in when I was in grade 3, I don't think that was possible. But when we were in grade 6, there are those negative numbers, so those are also important. And then we were introduced to also the concept of fractions. We can divide. So basically, rational numbers are just numbers that can be expressed in the form of p over q, where p and q are integers and q is not equal to 0. So those are rational numbers. But there are also numbers that are like, for example, if you have a length of 1 and a triangle with a right triangle with a length of 1 on both sides, and you want to know the hypotenuse, the length of the hypotenuse, that's not actually a rational number anymore. That's actually an irrational number. So that's a square root of 2. And there are also some numbers that are uh, also important in mathematics. That's not also a rational number, or it's not also an algebraic number. It's called transcendental number. So we have those pi and e. So those are part of the real numbers. But sometimes it's also important. There are some applications where it's very important to invent another kind of number. We call that the imaginary number. For example, this imaginary numbers and real numbers, if you combine them, they are basically the complex numbers. So imaginary number, the idea is, for example, if you want to know if you want to solve equations wherein, like, for example, x squared plus 1 is equals to 0, okay? So there's no real number that can satisfy that equation. So but sometimes those type of equations are important, and we need to invent numbers to actually satisfy those, like x squared plus 1 is equals to 0. So we have to define numbers like this, called imaginary numbers. And so basically, complex numbers, they are in notation, we can represent them as, commonly we represent them as the number as letter z, and it has actually two parts. It can be represented as a plus b times I, where I squared is equals to -1. So this is, it has two parts. This one is called the real part. A is the real part and B is the imaginary part. So these are examples of complex numbers. Z, 3 plus 2i, and W, -4.3 minus 2i. This one are also called complex numbers. This one, x equals to 6, is also called complex number. So as you can see, all real numbers are complex numbers. All imaginary numbers are complex number. 0 is a complex number. 0 is a real number. 0 is also an imaginary number. Okay, so 0 is both real and imaginary. Because if you're going to this one is called an Argand diagram, or the Gauss. We usually geometrically we can represent a complex number by for example, in this case, a point here or a vector, okay, wherein you can see the x-axis is the real axis and the y-axis is the imaginary axis. As you can see, 0 is here, so 0 is both an imaginary number and a real number. But every point here is a complex number. Any complex number can be represented in this Argand diagram, or in this Gauss plane. Okay, this is called a Gauss plane, or an Argand diagram, where geometrically we can represent any complex number. A is the real part, B is the imaginary part. So this is the Cartesian form. We can addition of complex number. So it's just straightforward. You just add the real part, add the imaginary part, and then append the I on the imaginary part. So that's addition. Subtraction is straightforward also. Example, this one, 5 plus 4i plus 7 plus 2i. So 12 plus 6i, and then negative 6 plus 3i plus 5 plus I, negative 1 plus 4i. So I plus negative 5 plus 6i. So negative 5 plus 7i. So geometrically, just like in vector addition, you can visualize addition of complex number just like the way we visualize vector addition. So for multiplication, it's just like the way we do binomial multiplying binomial. We use FOIL. Okay, the first, outsides, insides, and last. So in this case, 5z plus 5 times 2z plus 7, 6z squared plus 21z plus 10z plus 35. And then since so in this case, you can see here, if you do FOIL, you will have the i's here that can be combined, and you will have I squared here. You have to change I squared to negative 1. So basically, this will become a minus sign. So yeah, using the FOIL method. For example, we have this 3 minus 4i plus 4 plus 5i. So 3 times 4 is 12. Negative 4i plus times 4 is 16. Negative 16i. 3 times 5i is 15i. And then you have negative 4i times positive 5i is negative 20i. And then substitute. So there you go. The answer is 32 negative I. Okay, so I forgot to mention about division. But for division, what you do is, for example, you have two complex number. Before we do division, let me just discuss conjugate. So complex conjugate, when if you have z, a plus bi, the complex conjugate z star is just a minus bi. So you just have to negate the negative part of the imaginary part of your complex number. So this will be very useful for division, because if you have to divide, you just have to multiply that ratio by the by 1. So express that one as the complex conjugate of your denominator time all over the complex conjugate, all over the complex conjugate of the denominator. So basically, I didn't have an example here, but the thing is, that the trick for division of complex numbers is you multiply it by complex conjugate of the denominator divided by the complex conjugate of that denominator. So basically, you're just multiplying it by 1. And then you do the multiplication, numerator to numerator, denominator to denominator, and then you can simplify. For the another important property of complex numbers are the absolute value or the modulus. So basically, the absolute value of or a modulus of a complex number is equals to the square root of the product of that complex number to its complex conjugate. So this is also the same as the real part squared plus the imaginary part squared, and then you get the square root. So for example, the modulus of 5 plus 6i is just the square root of 5 squared plus 6 squared in this case. So square root of 61. So modulus is always a real number. So exercise modulus of 3 minus 2i, modulus of I, modulus of 6 plus 3i. Okay. So this is division. So for the technique for the division is you just multiply it by the complex conjugate of the denominator, and then you do the numerator times numerator, and then denominator times denominator, and then you simplify. So example, this one, 2 plus 5i divided by 4 minus I. So the complex conjugate of the denominator is 4 plus I. So basically, you're just multiplying by 1. And then you numerator times numerator, you have this one. And then denominator times denominator, you have that one. And then you simplify. So you will end up with this one. 3 over 17 plus 22 over 17i. Exponentiation of complex numbers. So I0 is equals to 1, I1 is equals to I squared is equals to negative 1, I cube is equals to I squared times I, so that's negative I. So it will just repeat for, it will just cycle with this sequence. So you have I4 going back to 1, I5 going back to I. So this is just a cycle, okay? So if you have that, okay, you have, you can now get the pattern 1, I, negative 1, negative I, 1, I, negative 1, negative I. So question, what is the value of I raised to the 100? Anyone? What's the value of I raised to the 100? Anyone from the students? Can you get the pattern here? Okay, I raised to the 100 is equals to 1 because 100 is divisible by 4. Anything divisible by 4 that whose power is divisible by 4 is always equal to 1. 0 is divisible by 4, 4 is divisible by 4, 8 is divisible by 4, 100 is divisible by 4. So the answer is 1. Next. Okay, we can also represent a complex number using polar coordinates. So this is if you're already familiar with polar coordinates. So for if the Cartesian coordinates or the rectangular coordinates, we represent it by x, y. In polar coordinates, we represent it by the radius and the angle that it forms on the x-axis. For example, this is your point in the Cartesian coordinates. So this is x, y. But we can also represent this by two numbers, the radius and the angle. Okay, so they are theta. So for the complex number, if using the Argand diagram, using these identities, r squared is equals to x squared plus y squared, and tangent theta is equals to y over x, we can transform any complex numbers written in the Cartesian form to its polar form by those formula. So for example, So this is the formula for the R, and the theta is also called the argument of that complex number. So cosine theta is equals to the real part divided by the modulus of the complex number. Sine theta is equals to the imaginary part divided by the modulus of the complex number. And tangent theta, of course, is just the ratio between of sine and cosine. So for z is equals to a plus ib, where r is equals to the modulus of z, a is equals to r cosine theta, and b is equals to r sine theta. So this is the polar form of a complex number. So for z is equals to a plus vi, for the polar form, z is equals to r cosine theta plus r sine theta. Sometimes they in some books they shorten this to cis or cis theta. Example. Okay, multiplication and division in polar form. For example, you have z sub 1 r1 cosine theta plus I sine theta, and z2 r2 cosine theta plus I sine theta. So the product of this is just the product of the radius and the sum of the arguments. And for the division, just the ratio of the two radius and difference between the two arguments. This is an important theorem, the De Moivre's theorem, that says that for exponentiation or for the powers of a complex number, you can actually generalize that to z to the n is equals to r to the n cosine n theta plus I n theta. So this is the De Moivre's theorem. And this is the most beautiful equation in all mathematics. E to the I pi plus I is equals to 0. So basically, can be derived by the exponential form of the complex number. Can be derived that this one here, cosine theta plus I sine theta, is just the same as e to the I theta. If you have already taken calculus or Taylor series expansion, you can see that the expansion of the Taylor series expansion of the function e to the x is just the sum of the expansion of cosine and sine. So you can actually derive this formula. And from there, this is the Euler's formula, and it is said to be the most beautiful equation in mathematics because it has all the important constants here and the important numbers like 0, 1, the important number, the important constants, the base of the natural logarithm, the imaginary number, and pi. So this is that's what makes mathematics very elegant and beautiful. Conjugation. Let me just. Okay, for multiplication of complex numbers using the polar form, basically, the product is just the product of the radius and the sum of the arguments. This black sphere will be discussed by my colleagues later on in the lecture series. But let me just breeze through the probability. So, and also an important concept in mathematics that will become very useful for quantum computing is the concept of probability. So basically, a probability is just a representation of the likelihood of an event, the likelihood of a event occurring. So it's a number between 0 and 1. So the probability of an impossible event is 0. The probability of a sure event is 1. So, and probability of an event is a number between 0 and 1. So those are the important definition of probability. And another thing to note is that basically, a random variable is a variable that we assign. It's a function that basically we assign a number for that the value for that event. For example, in this case, if you have two coins, tossing two coins, so you can actually define a random variable, in this case, the number of heads occurring. So that's a random variable. And then we can assign a probability of it for an event to have that value of a random variable occurring. For example, in this case, a random variable values are 0, 1, 1, and 2. So meaning it represents the number of heads na turn up during the tossing of the two coins. So this one, HH, is no head. HT, one head. The first coin turns up heads, the second turns up tails, and then this one, the second turns up heads, and then this one, both of them turns out tails. So, this random variable represents the number of tails, not the number of heads. So we can assign a probability for each of these from happening. For example, if these events are equally likely, we can assign the number for the probability of S equals 0 as 1/4, since it's 1/4, and for probability S equals 1, or the random variable equals to 1 to be 1/2, because there are two events or two values that appears out of the four, the four number of that's the sample size, the number of the sample size, and P of S equals to 2 as 1/4. So basically, as you can see, all of these numbers are positive. All of these numbers is a number between 0 and 1. And another important property of a probability distribution is they must sum up to 1. So those are the important thing to know in probability theory, RN. So you have the concept of random variable. So a random variable basically is a variable that you assign, a number that you assign to an event or a process. And then each of these numbers has some probability distributions. Okay, so in this case, we assign probability distributions of 1/4 for S equals 0, for 1/2 for S equals 1, and 1/4 for S is equals to 2. So that's an example of a discrete random variable. But sometimes there are random variables that that is really impractical to enumerate because they are continuous. So in those cases, you will have to use calculus, or to actually come at calculus to compute for the probability distribution of those kinds of random variables, for continuous random variables. And an example of that is the Gaussian distribution. But in this case, these are examples of discrete random variables. As you can see here, this is a random variable that denotes the sum of the outcome of when you roll two dice. So these are the possible sums. It ranges from 2 to 12, and each of these values has corresponding probability distribution. And if you total this probability distribution, they should add up to 1. Okay. And another concept in random variables, the concept of expectation, or the expected value. So basically, it's just a weighted sum, meaning the probability, you get the expected value of a random variable by multiplying the value to its probability distribution. So you can think of this as the concept of linear combination. As you can see here, this is a linear combination. You multiply something and then you add another, multiply the probability to its to the random variable value, and then you get the total for all of the random variable value. So that's the expectation. Then there's also So in this case, the expected value is 3.5. If you did that for the dice example. Uh, okay, so there's also what we call the variance. So there's also variance of a random variable is just the expected value of the squared of that random variable minus the expected value squared. So yeah, that's it. Sorry, it took a lot of time, but that's just a breeze through or of a rundown of some of the important mathematics that we need to know. I'm sure there's a lot of things that I haven't covered, but some of my colleagues will be able should cover them along the way in their respective lectures. And thank you for listening.
Thank you for that, Sir Elmer. Ayan, let me just share my screen. Okay. So I was reading upon the chats sa Discord. So some are overwhelmed. I noticed rin on some temperature check kanina that as the ano yeah, pero we're very thankful po Sir Elmer for that very in-depth. Like ako personally, that's our lesson on my classes right now, and I gained some insights on that. And aside from that, guys, it's okay if you feel overwhelmed right now. Especially if these concepts, mathematical concepts, are new to you. So don't worry. We will send you a lot of resources for that. Also, tomorrow, me and Lance would be on Discord. So chat na lang namin kayo on what particular time. Pero yes, we would have like an hour or an hour and a half just to go back to some of the lessons and even solve some of the problems and exercises. Okay, so we said earlier that we're gonna have a review then on Python and getting started with IBM Quantum, but yeah, we took quite a lot of time about that kasi super important kasi nila, right? We're talking about all of these mathematics, and hindi naman sila tinuro ni Sir Elmer sa atin for nothing, 'di ba? So this would be the fundamentals for the next lessons. Okay? So at this point, I would like to ask everyone to open your cameras so that you can take a photo. Hello, hello. Ayan. So, okay. Mukhang nag-iisip sila, mukhang ano, gamit na gamit ang brain cells natin na ayan. Sige. So, did you had your dinner na ba, guys? Ayan, so kanina I was eating while nagdi-discuss si Sir. Pero ayan. Okay. So, let me ask someone else rin po to capture the screenshot, Sir Elmer. O- Okay. Sige.
Elmer, are you still there?
Yeah, I just took. I'll grab another one. Okay,
Okay.
ready? Yeah, yeah.
Smile, everyone.
Wait. Okay, the count of three. 1, 2, 3. Wait. There's a lot of. I'll just use the next set of because there are five. Cannot capture everyone on screen. So this is the next set of students are 1, 2, 3. Smile. Okay, next one. Okay. So some are not opening their cameras yet. Okay. 1, 2. Okay, last one. Okay, I have already captured everyone
All
on
right.
camera. Yeah.
Okay. Thank you po for that. And at the end of our lecture 2, so we would ask everyone to fill up this form. Wait, let me just copy the form and for your attendance. So remember everyone na you would need to attend at least 4 of our lectures. And of course, the offboarding, the last lecture on October 19 is mandatory, or yeah, we need to attend that one. Pero yeah, please check your attendance there, and of course feedback rin, so that we can better suit, or we can better cater you on our next lectures. So actually meron yang ano, wait, let me just remove some of the ano, second. Let me just remove some of the ano, kasi meron yung Python review and getting started with IBM Quantum. All right. Sige. Okay. Okay. So please just fill up the form, attendance and feedback form. It will close within an hour. So yeah, up until 8 o'clock, I will close that form. So if you want to get some certificates, yan, short ano lang yan, short attendance and feedback lang naman. All right. So again, thank you very much for tonight. Maraming salamat po, Sir Elmer. Maraming salamat po,
Maraming salamat kay
everyone.
Elmer.
Maraming salamat
Thanks,
everyone
Thanks
for
Elmer.
attending.
everyone. Thank you.
Okay,
Bye.
so we'll just send a message kung anong oras tayo pwedeng mag-study lecture or study sa Discord tomorrow. And yeah, you can prepare your questions na doon. All right, again, thank you very much. You can leave the call now after you've filled up the attendance and feedback form. Bye-bye. Sige, see you next week or see you bukas. Okay.